mode. Okay, so I'm going to talk about serialization, which is something that sort of we've been fiddling. We end up fiddling with this. We've fiddled with it in Parsl over the years, and in the last month or so, I've been digging a lot deeper into it. So I made this presentation with some thoughts about what's happening. So do you have a big gray box in the middle of your screen here or not? Because I do. Do you see
Yes.
where my place? Yeah, you do.
Well, not a big one, a little.
Can now see your screen.
Yeah, that.
Yep.
Oh, it's a bit. There we go. It's fading away.
Very
Okay.
slowly.
Okay. Hopefully it'll be gone in a minute. Okay, so I'm going to talk about how object serialization works in Parsl at the moment. I'm going to talk about why we might want different serialization mechanisms, because we've tried different things over the years. I'm going to talk a bit about the prototype for letting users plug in their own mechanisms that I've made. I'm going to give an example using this thing called Proxy Store, which is from another group in Chicago. I'll talk about some terrible problems I encountered and path forwards. So one thing that's characterized everything I've seen about us doing serialization is we keep thinking it's easy, we just need to find the right library and then everything will be fine. And then we try a different library maybe, and it's just like push down one bump and a different thing pops up. So if some of this seems very complicated, it's because it is. Okay. So I'm going to start at sort of basics of Parsl. How do you invoke a function? So if you're in Python, no Parsl involved, what a function invocation looks like is basically this. You've got two objects. We've got an object A, which is a function, but it's just an object. And we've got an object B, which here in this case is an integer 1000. Again, it's just an object. And we sort of smush these two objects together with the syntax at the bottom of the screen to cause function application. And hopefully that output of 1001, 1001 is not particularly surprising if you can read that code. So when we do that in Parsl, what happens is we overload function application using the Python app decorator. So when you write A bracket B, close bracket, and put them together, that doesn't result in function execution. What it results in is the object A and the object B disappearing into the guts of Parsl, and Parsl decides what it's going to do with those. So the idea is it will eventually evaluate them, but Parsl is going to be in charge of deciding when that happens. And if you're using something like the high throughput executor or work queue, what will happen is those objects will eventually end up on a worker, and on the worker, they get put together and evaluated. And then there's a result object, and the result object finds its way back to the submit side. And that's what we give to the user. So that is pretty straightforward, apart from, well, for the purposes of the talk, there's just one problem. You can't send objects to other processes. Objects live in a particular process. You can't just move them to another place. So instead, what we try and do is get another object on the remote process that is somehow like a ghostly image of the original object. It's not the same object, but we hope that it's same enough to behave as for our purposes. We hope that it'll behave close enough. So the example here, process one, we've got an object which is that contains the integer 1000, and the ghost that we make on the other side, that ghost object, well, on the submit side, we know if we add 1 to 1000, we're going to end up with 1001. So we would expect on the remote side, if I add 1 to this ghostly object, the ghostly image, I would end up with 1001 as well. And so this ghostly projection is what serialization is, serialization and deserialization. We're trying to make an object on the remote system that is same enough as the object on the submitting system for everything to work, but it isn't the same object. So if we look at that,
Yeah, hey, Ben, sorry, I think you
Hi.
can't see hands probably very easily, so I'll just jump in for a second with
Yeah,
but I don't want to take you to an hour of talking. But just really quickly, like in terms of other languages where there's like pass by reference and pass by copy, can you think of this as just making a copy of the object, or is that too simple?
it is too simple.
Okay,
Give me like give me 2 more slides.
okay,
And I'll come to that. Okay, so in the Parsl case, this is that invocation pattern we had before. We've got F and X, and we make the ghostly copies on the worker. We by serializing those 2 values. Actually, we serialize a lot more, but for this example, we just serialize the function and the object and the parameters. We invoke it there, get the result object. We magically transition it back to the submit side. So that's sort of moving through space. There's also in Parsl another dimension in time that if you're doing checkpointing, we now need to also project that image into the future to whoever in the future is making that same function call and wants to reuse the result. Okay, so these are the sort of paths of serialization in Parsl. So in the big thing that Python uses is this thing called built-in library called pickle. And the way you get things between processes is you can pickle an object using pickle.dumps, for example, and that will give you a byte stream. And the assumption is that you know how to get a byte stream from one process to another. Pickle isn't trying to solve that problem for you. And then when you have the byte stream over on your other process, you can say pickle.loads, and you get this recreated image of your original object. And pretty much all the serialization that we do is based around this pattern in some way. So I'll give you some examples, 3 examples. Here's a really simple one. Just the number 1000. So you run the code in blue and it will write a file called slideware.pickle. And if you run this beige box over here, it'll unpickle it and give you another object that contains 1000. What's actually happening here is pickle is a like a virtual machine language. So dumping a pickle actually writes out a little virtual machine program. Here's the hex code for it, and you can run, there's a built-in disassembler for it. So here's the disassembled version of what that little virtual machine program is. And so what this is a program to create an object that is like the object you started with. And here it's pretty simple. It says, this is protocol version 4. The rest of the program is 4 bytes long. Push the literal integer 1000 to the stack. That's it. We're done. Okay. That's pretty straightforward. So for a lot of data that is, for a lot of objects that are like data-like, so what you imagine a sort of struct in C, it's just integers, strings, lists maybe. This is very straightforward. It's very rarely a problem to dump stuff out. And all the problems come with more complex, or most of the problems come with more complex objects. So one sort of medium complexity object is a dictionary. So if we pickle this dictionary, A to 1000, A maps to 1000, B maps to 2000. So one thing that we have to do is pickle is going to work recursively. So in order to construct this dictionary object, first it's going to have to get copies or ghostly images of these 4 objects. So it will recursively pickle A, B, 1000 and 2000. And then the reconstruction program can say, right, here's how you build A, here's how you build B, here's how you build 1000, here's how you build 2000. Now, the final result object is this dictionary made of those 4 values. And in general, that can be a directed cyclic graph. It doesn't have to be acyclic, it can be arbitrary depth. So structures like this can be pretty complicated. And pickle will just recurse through and remember what it's pickled. 2 problems that happen here, which are a bit more problems with sort of equality in caching maybe than specifically with serialization, is, for example, this structure Y, is this equal to structure X that we started with? And if it is equal, Python will tell you that it's equal. If it's equal, can we tell them apart? If I run this expression and this expression, we might hope that we get the same value. In fact, we don't. So every now and then we encounter caching issues that come from things like this, where we thought objects were the same, but actually they weren't the same, and that gives you weirdness. And then also a caching problem we had is with mutability. If you dump this structure out and then you deserialize it with a caching deserializer, so this is like a mini version of Parsl's caching deserializer. It will deserialize, okay, but then if we mutate that value and then deserialize the byte stream again, what actually comes back from that is non-deterministic, depending on what other cache activity the cache has seen in between these lines here. So that's another problem. And then the super weird one, which gives everyone loads of frustration, is functions. Pickle by default just takes a very simple approach. It says, I'm going to assume that I can just import a function remotely. So I'm going to assume that the source file is on the remote system, meaning, say, the relevant package is installed, or it's just sitting there on the file system. And then all it does is sends the fully qualified name of the function. And to deserialize it, you do the equivalent of import the module and then pull out the function name from that module. And that's the deserialized version. And that doesn't work in many cases. It doesn't work if you're defining stuff interactively in a notebook, for example, because there is no source file on the remote system to do the import from. So there's another library called dill, which is an extension of Pickle, which gives you a whole different set of problems. What that does is pulls the bytecode out of the Python compiled bytecode out and serializes it. And then when you deserialize it, it just uses the bytecode that it got from the originating system. So that doesn't work between Python versions particularly well. It tries to send other auxiliary class definitions and things like that it thinks you're going to need. And the worst case I've seen there is it tried to serialize the entire Python runtime into a byte stream because one of the heuristics was wrong. So you end up with this incredibly large serialization of all of Python just to transmit your one class definition. And the third horrible way is that you try and get the source code for a function, which is often a misassumption because functions often don't have source code. It's incredibly fragile. Everybody thinks it's a good idea to do it. I keep telling people, please don't do this, but every few months somebody does. I was the last time I asked someone not to serialize source code was yesterday. But it's just an incredibly fragile method. But if you are trying to get really simple functions to work between different Python versions, it's probably the only way that you're really reliably going to get that to happen. So it does have its use cases. So that's sort of Pickle and serialization in general. The way that Parsl works is it has a serializer wrapper library that has this policy around some of these different ways of serializing. So if you call, or in other bits of Parsl, will call into its own serializer library. And if you feed in an object, the first thing we ask is it a callable object? And then we're going to proceed down one of these two paths. And that asking, is it callable, is really a heuristic to say, is this the kind of object that is going to get used a lot? And it's not going to change, it's immutable, so I can cache it's worth caching and I can cache it. And so the assumption there is that I'm going to perhaps define a function and then invoke it 1,000,000 times on 1,000,000 different arguments. So it makes sense to cache the function serialization because I'm going to use it 1,000,000 times without changing it. And it's a bit of asking if it's a callable is a bit of a weird heuristic that I'm not particularly comfortable with, but That's what we do. So if it is callable, up until yesterday, it used to first try pickle with a cache. And if that failed, then it would try dill with a cache wrap around it. As of yesterday, it just tries dill because pickle was annoying me too much. If it isn't callable, then we just try pickle first and dill if that raises an exception. So one of the subtleties here is we only move on to the next serializer if there's an exception. So if pickle returns a value that's valid but isn't going to deserialize properly remotely, this isn't going to detect that. Okay. And one example of that is pickle doing these very naive function serializations. Using a name, it will still give you a name to import remotely, but that import just won't work later on when the value arrives at the destination. So that was the main motivation for removing pickle for functions. Okay. So why extend this? The basic extension is that you want to plug other mechanisms into that graph to try out different things. So the interesting cases that I vaguely have on my radar at the moment are there are different ways to serialize functions. I've seen at least 2 different ways, for example, serializing functions by source code. There's another library called Cloud Pickle, which is kind of in the same way that dill tries to make pickle better. It's also other extensions to dill, to pickle. There's a project called Proxy Store, which for the purposes of this talk, you can just imagine as a fancy way to convey and cache pickled objects. There's actually a lot going on there, but that's what it is from the serialization perspective. There's a lot of experimenting and fiddling with caching. There are lots of enemies to caching. So the internal enemies are our monitoring system, sometimes makes wrappers that are not very cache friendly. File staging will tend to wrap functions in a way that aren't cache friendly. And then we have external enemies, which are, of course, our users, who make some really interesting function objects using decorators and partial applications and things like that. And those sometimes aren't particularly amenable to being cached in the way that we're caching at the moment. And then a couple of other ideas that kind of fit in this space that I'm not intending to think about implementing, but they're sort of in the space. You could think about more secure serializers. So I've seen people talk about a use case where they want workers only to run approved functions, not arbitrary user code, for example. And pickle is a bad serializer to use in that case. Or there's things like remote method invocation, where you make a stub object which forwards invocations over the network to the original object, for example. So Java remote method invocation, all the rage in the 1990s, for example, with distributed stateful objects. That would also fit into this mechanism, perhaps. So the mechanisms that exist for extensibility at the moment, the Parsl serializer library, if you edit the source code, you can very easily add things into that flowchart that I showed you a few slides back, but you can only do it in one place in this one file, concretes.py, because of how it's implemented. So to add a new serializer, you have to fork Parsl and edit that one file. But then once you've made the choice to do that, it's pretty straightforward. A very lame proxy store prototype took about 10 lines of code and then some other tidy ups. But the big deal for user extensibility is you have to do it in a forked version of Parsl. You can't do it as a plugin in the same way that you can plug in executors or providers. The other big existing mechanism is Pickle. So Pickle has loads of plug points to change how things are serialized and deserialized. You can, when you define a class, you can describe how your class will be deserialized or serialized and deserialized. So by default, for sort of data-like objects, there's a default that just says take all the fields or the attributes of this class and make a new object on the remote end with copies of the same attributes. So for anything that it is like data, that's usually the sensible default. But the API is incredibly flexible. You can have it execute arbitrary code to produce the relevant remote object, for example. You can also override, you can basically say, here's a new instance of Pickle, and I want it to use my own reducer code, my own serialization code for particular classes for whatever reason. And one of the interesting things there compared to the Parsl serialization sort of selector is that when Pickle works recursively, it will run this dispatch on all the objects recursed, so you get to plug in and hook deep into a graph. You can hook in your own serialization methods. It's also got two things: out of band buffers and external objects, which are all about taking an object that you want to move through some external mechanism. So the external object mechanism is, maybe I just want to replace this object with a key and then have the actual meat of the object in a database somewhere, and only the ID key gets transmitted. And the out of band buffers is, you can say, here's a large buffer, and then a transmission mechanism can say, I know how to move large buffers in a different efficient way compared to however you're normally moving an object. So if you've seen proxy store, some of these will give you echoes of what proxy store is also trying to do. So the biggest example of this is DIL. DIL is just Pickle, and then they call these extension mechanisms to add a whole load of new data types. So DIL is basically implemented as teach Pickle how to serialize a load of stuff. But what comes out is just a pickled object. You can often deserialize it with Pickle because it is Pickle, for example. So I made, just as a proof of this danger execute arbitrary code, I made a little library called Pickle Run. And what it will do is it will give you a byte stream. It will take a function call and reify it and give you a byte stream. And then that function call will get executed when you do the deserialization inside the remote deserializer. And the result of the function is your remote object. So this was just me playing around, trying to understand what kind of mechanisms can you make for deserialization. So I wanted to understand that a little bit, and I just ended up with this. So the example here is I've made my function. It does a print statement and adds one to the parameter, and you invoke it with my func3. You get a byte stream that you can feed into Pickle. When you do the pickle.loads, it will print out I'm executing inside the deserializer. So the actual practical use of deserializers here is, say you need to do something other than just copying data, like maybe you need to resolve some handles or look up some DNS names or make network connections or start threads or something like that. You've got the ability to do that as part of the deserialization process. So I've been fiddling with two different ways of doing prototypes. The Pickle mechanism that I talked about exists already because Pickle already exists and is already used. And then I made a pretty simple extensibility prototype for plugging into that flowchart that I showed earlier, which is there's just a list of registered serializers. Starts with that's actually the usual 3 serializers now. And you can edit that list just by modifying this global list. So if you want to add a new serializer, you instantiate it and you add it to the list. And then on deserialization, Parsl imports the relevant deserializer and asks it to deserialize. So the downsides of that is it's incredibly awkward to test, in part because it's global to the whole process, and in part because the serializer mechanism, if you have an error, it just falls through to a different serializer. So your serializer can be completely broken and all your tests seem to be passing because it's actually using DIL, for example. Another downside is you can't change the return value serialization mechanism because you can't edit the worker side serializer list. I didn't make it do checkpointing serialization, but I think that's only a small change, but it happens to not do that. And I find the way that the code is structured at the moment is still a little bit weird, conflating classes and instances and serializers and deserializers. So that makes it a little bit hard for users to understand how they should be making a serializer. And the big problem is that serializer selection really only sees the top level objects, which I'll show next, which is actually what drove me to investigate the pickle extension a little bit harder. So what happens when you invoke a function? So here's a made up bash app called rescale, and you pass in a giant matrix and the number 100, and you invoke it again and pass in the giant matrix and the number 200. So the serializer call gets called 3 times. Once it gets called for the function, once it gets called for the args, right, which is a tuple, and all the args get sent to the serializer all at once, and once for the keyword args, which in this case is there aren't any. So it's an empty dictionary, so that's pretty easy to serialize. But the function isn't the actual function object inside Parsl. By the time it gets to being serialized, isn't just this little function that you wrote in your source code. It's it's a function object. It's got bytecode attached to it, not source code. It's been wrapped by, in the case of a bash app, and some wrapping to give it to make it have bash app behavior with this remote bash executor wrapper here. And then there's some error handling wrapper that's been added on here called wrap error, which is a function which has a closure which refers to all of this. So what serialize sees is this entire object graph. It doesn't get to, I mean, if you make a serializer, your serializer can inspect the object graph, but it's not a case of plugging in a serializer that says, I know how to do bytecode, because this call never gets called on a bytecode object. And then over here, serializing the arguments, it's given all the arguments in a tuple. So there's a tuple which has 2 things in it. If we're trying to cache this, we might want to somehow cache giant matrix because it's a giant. And that's what the proxy store use case, for example, is this. But again, in this case, it only gets called on the entire tuple. So even though I invoked the thing with giant matrix twice, it turned out that serializer saw 2 different things. The first time it will see this tuple, and the second time it will see a different tuple with the number 200 here. So that's not immediately cache friendly. So not cache friendly, not LRU cache friendly, not proxy store friendly. And that's what led me to look at plugging into Pickle, because actually I want to plug into the object graph and plug a proxy store hook in down here based on type. So I've got 2 proxy store extension examples. One is the top level, plugging into the top level selector. And this is basically the code you need. So there's a bit of boilerplate here. You can choose, is it going to go down the code path or the data path or both? It needs an identifier, but that's fairly programmatically easy to generate programmatically, so I'll probably get rid of that. And all we do is you pass in a store, but that's a proxy store object, and save it for later. When someone says, please serialize this data object, what we're going to do is make a proxy. We're going to register it with proxy store, and we're going to serialize the proxy instead. So then on the deserialized sign with proxy store, you just need to deserialize the proxy, and proxy store will handle everything else for you. Okay, so this is pretty straightforward. All we're doing is, this is basically boilerplate that comes out of the proxy store user guide, and I've just pasted it in a way that Parsl knows how to do it. Another example is this thing called Serpent, which is another serializer. So I thought I would just try it out. Again, pretty straightforward. You use serpent.dumps instead of pickle.dumps. Serpent is especially bad at trying really hard to serialize your data, even if it makes stuff that isn't going to work. So what I do here in this section is just try and deserialize it and compare it with the data we started with. because very often Serpent makes you some really strange looking object that isn't good enough. And this is a way to try and detect that. And the deserialization is serpent.loads. The other thing is proxy store, but embedded deeply hooked into Pickle. So you make a pickler. I extended dill here just because it's nicer than raw pickle, but it is pickle at heart. And you can override for every object how an object gets reduced. And I've said if it's there's basically a policy decision here that I made, and the policy decision is this a matrix or whatever. Then we're going to pass it through proxy store and reduce the proxy. And if not, we're going to say we're not implemented, and Pickle will go off and try the other mechanisms it knows. And it will try this for every object in the subgraph instead of just the top level one like Parsl, which means if the policy is to serialize every pandas data frame, then it will find if you've hidden a pandas data frame in your arguments deep inside a list of dictionaries of more lists, it will still find those data frames deep inside there, and the policy will be applied to them. And so I think this is the way forward compared to what I showed on the previous slide for a lot of differences. Yeah.
Quick question here. How are you defining all the proxy store stuff with the depickler? That's defined statically somehow?
Yeah, there's a little bit of, there's this, that's the proxy store here. So when you construct this, you have to pass in the proxy store.
Okay, well that's
so like
fine.
That's pretty normal. Like here, right? Self.store. When you construct it,
you're passing out.
You've got to pass in a proxy store already. This is all this is doing is wiring in. You'd read the proxy store user guide that will tell you how to make a store object. And then this is how you'll just wire that store object into the Pickle system, into the serializers. Okay. And the same here. The assumption is somewhere in this space here, you've done that. And I wouldn't expect Parsl to be doing that. I would expect the user to be doing that because it's going to be the user's choice.
So at some level, maybe we can outsource this piece to the proxy store guys. Like, why can't they implement this pickler for us? I mean,
wait one more slide.
Okay, go ahead.
Yeah. So there's two different proxy store plugins. Like I said, for that, I prefer the pickle style because you can get really into the object graph, but it's a little bit more nuanced and more confusing. So if you've been staring at serializers for months, it's like, oh yeah, this is obvious, but maybe not so much. The other top level stuff is a lot easier to just stick a new thing in. The future is, all right, I think this is a prototype API, the top level API, it's fine to go into master now and just say it's a prototype API. If you use it, expect it to change because it's not going to affect existing Parsl users who don't use the API. I think the proxy store serializer stuff is simple enough to go into Parsl, or as Kyle said, maybe into proxy store. And I think that will take a week or so. The main achievement there Kyle will stop complaining every week about proxy store not being integrated, and he can help people use them together. In the future, there's all kinds of issues that I talked that are big or small through this talk. There are things to think about. I really want to encourage other people to play with this. You can put stuff in the Parsl code base. You can put stuff out of the Parsl code base. That's the whole point of the API, is to let you do stuff outside of the Parsl code base. The things that really interest me are, what can we do with this policy-driven pickle style proxy store stuff? I've had a play, like I showed you 2 slides back. Could you do more interesting caching deeper inside the object graph? I have a feeling there's something interesting there, but I'm not quite sure. I think it's a better fit for really complex Python structures, not these sort of children's style structures that I've had in these slides. With people who have much more complicated stuff, I think that's a better fit. And then from a sort of production perspective, how do we characterize its behavior? How the behavior of different serializers? How do we benchmark them, for example? How do we know if they're actually working? Failures often just become a performance problem. like cache misses, for example, or if your serializer is broken, it just uses a different one automatically for you. So it's often not incredibly obvious when something is going wrong. And I'm not sure how and what we should do about that. And that's the end.